I think Japan Geosciences Union, so JPGU, it's actually a joint meeting between AGU and the Geosciences Union. It's going to be at the end of May, 24 to 29 May in 2026. I'm considering putting together a session proposal. They're due October 15th. And I think this is a nice group with this kind of focusing topic potentially on global floods or GEWEX related topics. So if there are those here interested to possibly collaborate, feel free to, say so now, or we can, send me an email and we could kind of go from there. I know it's a long way for most people.
Yeah, absolutely. So, I mean, we can send an email out to the email chain too, so that those who couldn't make it today, there might be some out there that would be interested, especially with the time, of when this is globally. It doesn't work for everyone. So, yeah, awesome. Well, thanks for bringing that up, Ben. And we're glad to have you here today to be our keynote speaker. So Ben Livneh is an associate professor at the University of Colorado Boulder. And he's going to present some of his work on global floods, but I'll let him introduce his topic. So hopefully you can share your screen, and then we'll have some questions afterwards. So
Let me make sure I can do that. Okay. Oh, I'm going to, oh, there's a problem.
there's always a problem with
Yeah, my Zoom just updated or something happened where now I have to quit and reopen. Shoot. Okay, so I'm gonna
right. Yeah, that's all right. We'll wait for you. That happens to me all the time. It updates, and then you're like, oh, right, now I got to restart. Yeah,
I'll be right back.
sounds good. Nope. In the meantime, anybody have any other things? So somebody put something in the chat. I'm at the Cortex meeting in Japan in March. Yeah, okay. So, yeah, if there are folks that may be going to the meeting in Japan in May, could be cool to have a good GEWEX flood session there. We've got a nice group with everybody, so it'd be awesome. And if you know somebody that may be not on the call that would be interested, please forward that to them also. Good to see you again, Ben.
Yes. Good to see you.
All right, looks like it's working. So,
And you can hear me okay? You can see my screen?
yep, looks good.
Okay. Well, thank you so much. Organizers, Josh, Vidya, and others that made this happen. Thanks everybody for joining. Before I start, it's around 7 o'clock here, and my kids are about to go to school, so there is a chance we could get a surprise visitor, but don't fret. Anyways, yeah, thank you for the nice invitation. What I'm going to talk about today, I thought was relevant for the GEWEX Crosscutting Initiative on flooding, and think a little bit about what's happening before flood events that might help us predict flood risks. So things related to precipitation timing leading up to flood events. Okay, so I think this group in particular doesn't need to be convinced that flooding is an important hazard. I'm showing a picture here from um, the floods that swept through Yellowstone National Park in the United States here in the year 2022, washing out a road. So clearly, these are very impactful events that can really create visible impacts, also damaging other infrastructure, human life, and things of the sort. So, um, what has often been regarded as, say, the driver of flooding is heavy rainfall, which is probably not surprising. And there have been reports of increases historically, as well as projections for future increases in extreme precipitation, which raises the question of how significant are future flood risks. And so it turns out that heavy rainfall is actually less explanatory than might be expected. And I'm really drawing on some nice work from another one of your organizers, Conrad Wasco, Ashish Sharma's work, and others that started looking at this about 10 years ago. And what they tried to understand was um, how strong is this linkage? So what I'm showing here is um, a, a graph of conditional probability. So given that you've had an extreme precipitation event, precipitation at the 99th percentile or higher, what is the probability that you will get an extreme flow event or a flood? Flow at the 99th percentile or higher. So P um, 99, Q99. And it turns out that this is much less than unity, which is kind of surprising. And I was certainly surprised, which is kind of what got me into this, interested in this in the first place. So only about a third or 36% of the time in their study of 438 basins, this was across the US, using gridded precipitation and using simulated discharge. I think it was from the Vic model that this study used. And so um, what it turns out, though, that a wet catchment is much more likely to produce flooding than a dry one. So, as hydrologists, we've known this for a long time that you can have soil moisture conditioning if the antecedent conditions are wet versus dry. Okay, so great. So this kind of confirms what we knew, and it raises the question then. So, what actually causes a catchment to be wet versus dry in the first place, right? And so a couple of things can do this. So first, probably at the longer time scale, is this, you can have long-term drying trends. This could be due to warming. It could be due to an elevated vapor pressure deficit in the atmosphere. This is an example for the United States, or seasonal or annual drought that could be causing catchments to be dry or wet. I guess the opposite phase of this. So a lot of this drying work has actually been focused more at the time scale of, climate change of years or decades. But what I'm going to argue in this presentation is that precipitation intermittency can actually dry soils on much shorter time scales. So this is just simply, let's say, the time between consecutive storm events at a particular location. Sometimes this is called the dry spell length. Similar measures are called the interstorm arrival time or the interamount time. And it turns out that the time scale of this is perhaps, so an e-folding time has been proposed of between maybe 5 to 20 days, certainly less than 20 days, to reduce the soil moisture by a factor of 1 over E. Some work done by McCall et al. In 2015 using the SMAP, the NASA SMAP satellite, kind of showed this map. Other observational evidence suggests that it might be slightly slower or slightly longer using land models and other things. But you can kind of see that, okay, so for most of the globe, the soil can dry out quite quickly. And my interest here is how would this be affecting flood risks in a much shorter time interval? So if we stay with um, precipitation intermittency as the time between consecutive storm events, we pulled together data for this watershed, the Little Washita watershed in Oklahoma. This is a basin that's been studied a fair bit. And what I've got here on the left vertical axis is the soil moisture through time, one measurement or observation from the SMAP satellite that I was showing before. Another one is from this ERA5 land model. And on the vertical axis, or the right-hand axis, and on the top here is the Haida graph, which is the rainfall itself. And so what you can see is that when there is a rainfall event, the soil moisture goes up, and then it kind of decays in almost an exponential way. And that's why you often see these e-folding timescales as being helpful for quantifying that. And you can clearly see this through time, and that the shorter the interval between rainfall events, generally the higher the soil moisture will be. And if we pair this graph with the stream flow from that watershed, we can see quite a dramatic difference for these two storm events, Storm 1 and Storm 2, which I would say are somewhat similar in magnitude. And yet, because Storm 2 is falling on much wetter soils, or stated kind of in the context of this talk, has had a much more recent rainfall event, so a much shorter intermittency. You can see here the flood potential is much higher. And so in this presentation, I want to take this concept a little bit further, and I want to define intermittency in the simplest possible way, which is just the time since the last rainfall, even though I recognize that others have defined this using other measures like the relative frequency of rainfall, for example. But we're going to just define it as simply the time since the last rainfall and see how well that predicts flood magnitudes. So stating this maybe a little bit more formally, our hypothesis is that precipitation intermittency can serve as a flood modulator. And, if we look at the top here, a situation of frequent precipitation, so going left to right through time, each storm event sort of recharges the soil moisture, then there's a gap, then there's a recharge. And so that's going to produce much wetter conditions at the time of a flood storm, which is what we're defining in this study as the large storm event, separate from intermittency, but the actual kind of triggering storm event, as compared to the lower case where we have more intermittent precipitation, where soils have time to dry out, and then a flood storm will be much less impactful and much less likely to produce a large flood event because there has been this longer duration. So to analyze this, what we did was we pulled together over 100 minimally regulated study basins. We required them to have at least 50 years of observational data. As you know, floods are very rare, so to have enough sample size to look at this, we needed a long record. And you can see the basins down here, colored by the number of years for which we have station-based precipitation from the Global Hydroclimate Network, as well as discharge. And you can see that we have in this histogram a lot of basins with more than 50 years, even a lot of basins with more than 70 years of paired precipitation and discharge. So this was a really useful data set. And then we repeated our analysis using gridded precipitation and simulated discharge from AERO5 land, kind of to be more similar to that image I showed you at the beginning from those earlier studies. Then we use this automated flood and storm identification technique from Zhang et al. From 2021, and we transform both the precipitation and the flooding into percentiles so that we could compare different locations with one another. As you know, flooding is highly nonlinear, and so the magnitudes can be so different that we needed a way to intercompare, and transforming into percentiles was the way we chose. So we did this a couple ways. So first, the first result I want to show is based entirely on the observations, the gauged precipitation and the gauged discharge. So what we have here is a graph of all of the floods that are at the 99th percentile or higher from our 108 basins. Okay, every point represents a flood event. And the horizontal axis is the intermittency, or the days before that flood event of the previous precipitation event. Okay, and we define this term lambda here to be this ratio of the percentiles. So the denominator here is the percentile of the precipitation, the flood storm associated with that event. And you can see here that we have a range of these. So the warmer colors show the truly extreme precipitation events, whereas the cooler colors show less extreme, so 90th, 92nd percentile. So what can we take away from this? I guess the first thing is that and I'll just say the vertical axis is that ratio of the percentile of the flood event, which is 99th percentile or higher, versus the percentile of the flood storm. So what we can see is there's a range of these. So really this lambda says like how much did the flooding exceed or not exceed the precipitation. There's also a lot of noise here you can see, which kind of reflects some of the observational uncertainty. And what we can say more generally is that for shorter intermittency, for floods that happened after a more recent storm event, you can have a wider range of precipitation events that can cause flooding. You know, the smaller ones, the more medium ones, and the larger ones. However, as we move to longer and longer intermittency, so 15 days or 20 days since the last storm event, it's really only the truly extreme precipitation events that can produce flooding. And I think this makes sense because by that point, the soils would be quite dry. Um, and so we tend to see this kind of decreasing relationship with time. We see almost no points in the upper right here. And that's probably because of this long time since the last storm. But also it could be due to the smaller sample size. So there's just not as many storms or not as many floods that occur, maybe less than 5% we calculated after 20 days intermittency. So to try to overcome some of this, we transition now to looking at the modeled data for the same basins. Okay, so here what we've done, kind of similar to the first graphic that I showed you from Conrad Wasco's work and Ashish Sharma's work. What we're looking at is the conditional flood probability. So given, and this is done using the ERA5 land reanalysis, given that a P99 rainfall event has happened, what is the probability that you get a Q99 value? And we organize this now based on the time since the last storm event, based on the intermittency. And we see this nice negative slope, which is kind of what we expected in terms of it shows that with increasing time since the last storm event, the probability of getting a flood given high rainfall is actually decreasing. And what we would say is that what we're trying to understand more generally, so we hypothesize that the intercept here is affected both by the atmospheric components, you know, the propensity for heavy rainfall, as well as the land components governing the tendency for the land surface to convert heavy rainfall into high flows. And we were kind of thinking that the slope of this is primarily controlled by the land, which means that the processes that control the rate of soil moisture dry down. Okay, so to try to understand this a little bit more, we subset the data based on different covariates or predictive predictors, and I'll show you what we found there. So the first thing we found is that conditional flood probability is most strongly affected by things like soil field capacity and aridity. So what I'm showing here is all of those same basins, but subset by those with low or below median field capacity, blue, and red above median field capacity. And what we found is that high field capacity regions tend to have lower overall flood probabilities and are more sensitive to the intermittency slope. So why is this, right? What is it about the field capacity? So it turns out, and this sort of confirms our hypothesis, by the way, with the intercept and the slope, that, you know, for runoff to occur, you essentially have to, the soil moisture has to exceed the field capacity. And there's a bunch of complex stuff happening in the soils, but the field capacity is kind of one variable that encapsulates a lot of those. And therefore, this we think that the high field capacity, sorry, for example, the low field capacity soils are less sensitive to changes in intermittency because those are likely easily exceeded by many storms, even smaller storms. And so we think that intermittency would be less of a factor for the low field capacity, whereas for the high field capacity storms, it would require more or greater precipitation, and so they would be more sensitive. Similarly, actually, when we look at aridity, so the ratio of potential evapotranspiration to precipitation, we find that arid and semi-arid regions are much more sensitive to intermittency, and this is simply because those places would have soils dry out much faster, and then that means that the intermittency would be a higher sensitivity to governing the antecedent moisture. So actually, this sort of overturns our hypothesis that the slope is only an atmospheric or only a soil-driven phenomenon. It actually seems like it's caused by both the atmosphere and the soil. So the last couple things here, we looked at trends, and so the additional consideration here is that um, we looked at trends throughout our 73-year time period, and what we found is that generally speaking, the trends were small. But the tendency for trends was that, when you had intermittency getting shorter in some basins, that was generally associated with flood trends getting higher, and that the opposite was also true. Places where intermittency was becoming longer, was becoming greater, we had flood trends decreasing. Although this is a pretty noisy and not a very strong relationship in terms of the magnitudes here. We were thinking as a next step to use this uh, framework to try to validate climate models, because for better or worse, a lot of climate models are used to assess future flood risks. So things like the CMIP6 or otherwise, despite them not being potentially always best suited for that. So as an example of this, we divided parts of the Western United States into different subregions based on their geography. And for one of those subregions, for example, we looked at what is the current intermittency, how many days is it? We used a few different products to do this. And then we said, if we're going to evaluate the climate models, well, we can't use this high resolution. We actually have to recalculate intermittency at coarser resolutions. So going from whatever this is, like a 10-kilometer grid scale up to a 50-kilometer or even a 250-kilometer grid scale for the coarsest GCMs. And you can see that that actually impacts the intermittency, makes it shorter and shorter. And this is because the bigger the grid cell you're working with, the more likely it is that precipitation has happened somewhere in that grid cell. Okay, so to conclude and summarize, we showed that intermittency is an indirect measure of antecedent moisture, that this precipitation intermittency actually can control soil moisture at much shorter time scales than things like climate-driven changes or drought. We showed that intermittency can actually serve as a flood modulator, and I actually think this is maybe the most important point, that it can serve as like an alternative to just soil moisture itself, because soil moisture is really uncertain. The models we use, the observations are irregularly spaced and sparse. So we showed that, although there are considerable uncertainties, and I think a lot more work is probably needed to bring those uncertainties down, but this presents a promising pathway forward to potentially have an alternative to understand flood risks using comparatively less information. So I want to acknowledge my funding here. Also, most of the work that you saw was published in this paper that we published last year at Science of the Total Environment. And so, yeah, with that, I will thank you for your time, and feel free to reach out if you have any questions or ask them right now.
Yeah, even better, right? Thanks a lot. Thanks a lot, Ben. Yeah, it was really interesting. Great to see this. So I would love to open this up now for questions. This definitely aligns with a lot of the research interests this group has relative to thinking about floods from a climate perspective, and some of those aspects, particularly relative to prediction. So go ahead, Thorsten, your question.
Ivan, thank you. Very nice study. So I like the idea of using or looking at intermittency, particularly since the results you showed earlier with the satellite soil moisture, of course, is very problematic given the very shallow soil moisture estimates that you get now. So I was wondering whether you looked at intermittency and length of intermittency in relation to other variables, because of course, 3 days after a rainfall event in the summer is different than 3 days after a rainfall event in winter or in spring. And there are different kind of indicators of catchment wetness. Now, stream flow itself is a good indicator. than the different soil moisture estimates modeled or otherwise, and whether you considered sort of a combination to understand how the value, intermittency value, plus some additional information might be even a much better indicator now, considering whatever temperature or whatever and something else in relation to different variables that might indicate the wetness, and whether you try to, whether you can improve that slightly.
Yeah, that's a great comment, Torsten. Thanks. And I know that like part of this is kind of going really low tech from like, instead of running models and everything, we just went to like, what is the single variable? And yes, I think you're onto something there for sure. So like one of the things we looked at was how dependent is intermittency, even on just climatological precipitation. And it does seem that there is a relationship. Places that are wetter tend to have shorter intervals. There is definitely a seasonal component, and we tried to exclude places with a lot of snow because snow is going to kind of interrupt that timing. I think there would be some interesting work, though, to be done trying to pair it with other things a little bit. Like we did a bit with the aridity, showing that that kind of explains some of this. But I think there could be some other interesting catchment features that could be helpful here. I generally agree with that.
Yeah, I wonder whether you could even, for example, calibrate it on the decline in stream flow and use stream flow as an indicator of general catchment wetness index, and see whether a combination of intermittency plus some evapotranspiration indicator or so would actually give you even a very good overall predictive ability for that.
Yeah, the base flow recession or something like that would probably tell us a lot. That's a great point, because one of the challenges that we found when we used the gauges only is that, so we're trying to find a gauge with a long record. It's typically you have one in a pretty large river basin, and the question is, how representative is that one gauge of the entire basin? The discharge would tell you more about the integrated what's going on rather than just one. And that was a constant uncertainty of how do we know we're doing this correctly? Yeah.
Yeah, Keith Bevan and others used sort of stream flow as a antecedent moisture condition for flood forecasting quite well. So thank you.
Nice. Thank you. Yeah, thanks for the nice question.
Could I ask a question, Bridget Scanlon? So looking at the recent flooding in Central Texas, it was dry as a cork beforehand, and the soils are very thin. So I would think soil thickness is also important. There's almost no soil there. And sometimes if the soils are really dry, are they hydrophobic? I mean, is there... so some of those... So soil thickness would be an interesting factor. And then, you know, with extremely dry soils, maybe the runoff, the soils are so dry that they can't absorb the water. And of course, the intensity is so high, you know, that it can't.
Thank you, Bridget. Yeah, that's a really nice question. And I think that, that Texas flood kind of loomed large around here and in the news, I know, for a while. And I think that the dry soils is certainly almost its own category. When you get those almost dry and cracking soils in desert or like semi-arid regions, yeah, you can have almost a hydrophobic or really like a crust that forms. Although I think in the Texas case, it was more one of these truly exceptional intensity situations where just the magnitude sort of far exceeded the infiltration capacity of the soil, or it could have been both. But yeah, I think this kind of points us more to like an interesting experiment to set up a simple model to run that. I think that actually would be really nice in terms of what are the limits for a particular soil texture in terms of its ability to absorb. I was thinking in this that those models are there's so much complexity in each of these systems that I felt like trying to capture that with a particular model would probably fall short. And so therefore we went all the way to the simplest possible explanatory variable. But yes, that complexity is really fascinating. So thank you for asking about it.
Great presentation. Thank you for doing this.
Sure.
Ricardo, you have your hand up. You want to ask your question?
Yep, thank you. Hey Ben, no, thank you so much for the presentation. Hey Ben, eh, so first it was actually the first a little surprising how low the probability of having the flood associated to the rain, as you said, is low.
Yes.
So I have two comments about that. So the first one is if you can let us know a little bit about what the other factors that explain or that enter into the picture may have, may have been discovered or what are your thoughts on that? And the second one is that it didn't seem to me that the floods that were being produced, so you're comparing this 99 flood, but if you get, say, a 95% flood out of a 99% rainfall, that you're still in that world that, something big happened out of something big happening before. So maybe
Yeah.
you can expand a little bit on this idea of big floods. How do you define if there is maybe a window that you can expand a little bit around that 99 definition?
Yeah.
Yeah.
Yeah, and we kind of wrestled with this a little bit. I took this project upon myself over a pretty long period where I was just kind of quietly doing a literature review for a while. And then I finally settled on 99, and it really does make a difference. So this idea that we actually thought exactly about what you said is, first, what if we don't care necessarily about a one-to-one P99, Q99, but what if we just had anything above a Q90 or a Q95? And it does skew things. You do get more of these events, but you still don't get 100%. And so that kind of leads to the first part of your question is, what are the other factors? So another part of this is that we're using daily information. And I think a lot of times storms can be, especially these big storms, can be 2-day or 3-day storms. So if you were able to look at those storms in aggregate, that and then the flooding in aggregate, the challenge, of course, is you have to recompute the statistics for these percentiles now with a 2-day or a 3-day. So it does get a little bit mixed up, or a little bit messy. That's part of it. And then the other part, I think, truly is the capturing the catchment wetness correctly. And so this study that is shown here was done with like the Vic model, and then our study, which I'm showing here, is done with the ERA 5. And I think even still, some of the catchment wetness is, even though, the nice thing about a model is that everything is like self-consistent, but I think the timing of the flow, these are grid cells, 1D grid cells, and kind of aggregating all of that together, as you know, as you move up in scales, the timing and the transport is also an important piece. And I don't know that the soil moisture in these models is necessarily functioning in the same way as it would in nature when you have these large events, especially because a lot of these models are not really flood hydrodynamic models. They're more like land surface. I think it's also just kind of an open question, which is what I'm fascinated by and what I'd love to think more about, maybe with some of you, and like, how could we close the gap? Like, I think Torsten had some ideas and your ideas. So that's a great question. Thank you.
Yeah, thank you.
Awesome. Any other questions? So I had a question for you, Ben, about the trend. If you go to your slide with the trends.
And
Yeah, this one. I thought this was interesting. Did you look at this spatially to see like where these ones in like the upper left are happening and where those are happening lower right?
I feel like we did. Yeah, this is all of that is like part of our response to reviewers, actually.
Okay, yeah, cool.
Yeah. This shows the trends in Q99 only. I have others not handy for the trends in P99. But yeah, you can see a bit of a, what would it be, like east to west, or there's kind of like a central plains.
Central Plains, yeah.
where you and I are located, there seems to be increasing trends a little bit.
Interesting. Yeah, that's what I was wondering if there was like spatial consistency and like where that was kind of showing up. So I think that could be interesting to look at in thinking about this idea of intermittency and how things are changing and how that may be either making floods worse or, maybe less destructive. In some ways, I feel like we have less floods here in Kansas than we used to. Some of that could be just, regulatory stuff and how they manage the reservoirs. But yeah.
Yeah, that's true. And this is the thing, actually, the thing that I'd like to continue working on here is this idea that, okay, everybody says large storm events are getting bigger or an extreme rainfall is getting bigger. And I think that, that's generally true, although not everywhere, but generally true. But if climate change is having this drying effect on soils, or if none of even without that, if the time between storms is changing, all other things equal, that could be kind of this big modulator that maybe people hadn't been thinking about. Yeah, so I think each region is probably going to have some interesting features, and it'll actually be kind of tricky to quantify, but I think doable, and therefore maybe an interesting some interesting conclusions. And yeah, there's the management, which I'm not including here at all, but reservoir operations, stuff like that. Yeah.
Very cool. Thanks.
Yeah.
I got another question here from NHJF1. I don't know who that is. There we go. Awesome.
Sorry, my name probably obviously isn't on there. Yeah, I think there's some interesting ideas here. I think I mean, size of catchment obviously matters a lot, and I know Conrad's done work on this in the past, and Ashish Sharma, and this is also related to your intermittency question as well, in terms of I suppose whether your rainfall actually exceeds the effective rainfall when you take away potential evapotranspiration. So I know that their work specifically looked at this effect and found that there is quite a clear link between intensification of rainfall and increases in flooding for small catchments, for example, and for urban areas. And I guess you'd kind of expect that, right? Because the soil moisture in the catchment doesn't dominate on modulating that flood response or the antecedent conditions, because it's so small that you don't have to get that big a rainfall event to actually overcome that that constraint. But for very large catchments, I agree that this PET soil moisture type effect is going to dominate. So yeah, I mean, I don't know. I mean, I just wondered, with the issues that we have with climate models in actually reproducing that intermittency in precipitation and the extremes as well. I wonder whether this is something we can actually quantify at the moment. And I mean, you were saying you were thinking about looking at climate models. I'm just interested in, I guess, how you might start to look at that, whether you've got any ideas about how you might look at it.
Yeah, great question. I didn't catch your name.
Sorry, I'm Haley Fowler.
Oh, Haley. Okay, nice to chat with you. Thank you for
I haven't managed to come to one of these meetings for ages, sorry, because I've always been busy.
Yeah, I totally understand. So a couple of thoughts. So great points about catchment area. We were worried that actually for our observational analysis, the bigger the catchment was, then the less representative our rain gauge would be, because we just had one long-standing rain gauge. And so we actually organized some of the results by catchment area. And we didn't see a clear stratification. So the colors here are the catchment area, and then the vertical is like the flood probability. So we thought that, okay, that probably in and of itself is not going to be explaining why we have so much noise or whatever. But then when you think about the climate models, so we first had to basically, like I was showing here, transform or like rescale the intermittency itself, and things look like quite a bit simpler at the large scale. And we wanted to, originally I set up that we thought this would be a great method to compare with climate models, because it's kind of like normalized in some way, that obviously the climate models will have biases in rainfall, they'll also have biases in flooding. And so we actually did look at a few climate models, which I'm showing here. And probably to nobody's surprise, they're considerably different. Uh, the the intercept, if you look at the vertical axes, are quite different for some of the models, and the slopes are also quite different. And so this was just kind of the first look at this, how we might do it. And so it seems to me that there's a lot to be done with upscaling this, but I still think because the climate models, for better or worse, are being used, we have to figure out some kind of way to try to vet them rather than just taking, these ensemble means of whatever's happening and assuming that that's, and I guess this is a whole other thing. I actually led the CMIP6 task force funded by NOAA, where we tried to get at this like model weighting. Do all models, do you weight them all equally or whatever? But that's a whole other thing. So there's a lot to be done, I guess. But this might be one way to try to vet the climate models, at least partially.
Yeah, although, I mean, be careful about ERA 5, right? Because it's not observations, and there's lots of issues with it representing observations of precipitation, particularly in anywhere that's dominated by convective rainfall. It just doesn't do a good job, right? And a lot of the US is unfortunately, the extremes are going to come from convection and convective storms. And the other thing it doesn't do well, of course, are tropical cyclones, right? So all of those processes that matter, it's not going to capture the intensities or the intermittency.
That's true. And I also know that in the year 2000, there's like a discontinuity or something in the soil moisture in ERA 5 land, which would affect a lot of this as well. And we tried to account for that, but it was, just another, I think that's a great point. So there's the data, the data continues to sort of confound us here.
Yeah. Okay. Thanks.
Thanks for those comments there, Haley. And yeah, you also put something in the chat about how, like, thinking about convective permitting models. Have you thought about doing this with like the CONUS 404 data and looking at this intermittency and like comparing that with what,
Yeah, I think that's a great, the NASA LIS model is one that we have been kind of exploring, but I think the CONUS 404 would be more, well, I don't know as much about it actually, but are you saying it does, is it gauge based or it has like
it's a dynamically downscaled high resolution model run that people have looked at and used for doing evaluation. So Andreas Preen, who's been part of this group, was kind of led that. And now that he's back in Switzerland. But so it would be something that we've thought about doing some sort of like flood analysis with that. And that was sort of another kind of broader question I have for the group too, relative to this is, one of the goals of this flood working group is to come up with some good projects or work groups that we can put together and kind of try to tackle some of these problems. Something like this relative to climate models and things, your work, Ben, this is definitely up that alley of kind of the working groups we'd like to do, and we could get contributions from people from all over the world to try to look at some of these data and kind of the regionally specific stuff.
Yeah, I would love that actually, because, just more eyes, more ideas, and hopefully the foundation of this is straightforward enough that it would be conducive to, collaboration. I think that'd be great.
Yeah. So I'm not sure if others have comments or thoughts about that. Definitely an open discussion from the group in terms of like, our work groups. We kind of had some rough ideas, but like, hopefully as we start getting more presentations and can have more discussion, people can say, hey, I think we could actually break something off here. And so if folks are interested in trying to pursue something like this, I'd love to hear your feedback on that either now or send an email to us, and maybe we can start putting a working group together, folks that are interested in working on problems like this.
Well, you can count me as interested.
That's awesome. That'd be great. Great to have you for that. So anybody else have any comments relative to Ben's presentation, questions or about the working groups in general or progress?
I guess I'd be curious to know a bit about the working groups per your report.
Yeah. So Vinny, do you want to talk a little bit about our different working groups and where they're at right now? I don't know exactly. We've had some that have started and kind of worked a little
Yeah.
bit.
That's a good point, Josh. Yes. So we had different working group that led by folks, Haley is here. She was one of the lead, and Tristan is here. He was another lead. So we had really kind of interesting groups. We came together with some kind of ideas and break down the flood issue in like process understanding, modeling, and also risk and impact. So, and then based on that, we framed the proposal, submitted to GEWEX, and got approved. So we still would like to go to that working group unless you guys want to say, okay, we want to add like, we had somebody was interested to include AI simulations. So we would be open to the suggestions you guys may have. And then we are actually looking for a case study. So any of you, if you are interested to work on a case study in flooding and have like a brief kind of update on your case study, would be happy to have you every month in a project meeting. I think that would be a great idea. So initially thought, if folks thought, okay, let's work on Africa because there is less kind of research in that area, but we couldn't find actually good catchment where we have like good enough data set to run the model and do the analysis and all. So we are open to suggestions. And again, if you have any case study, funded project, would like to provide update in our meeting, we would welcome you to contribute. And also I put a report that a Google Doc or report, we collect different kind of publication. We start like framing the report. If you have, publication related to flood, I am sure you have a lot of publication, Ben. Feel free to add there so that we can include it in the final report. That would be great to have your contribution here. So yeah. Thank you for the nice presentations. I'm just mostly programmer and software developer. And I have all respect for people who do science and, kind of field work and all, but, I have my niche in. But we done quite, developing models for flooding here, but there's the kind of informatic and software development part of it. So.
I think that's what's good about this group too, is we all kind of have our little niches, and if we can bring that together, we've got good perspectives and how we kind of look at some of these problems and to make progress, I think. So
yeah, these are also the list of keynote speakers we had for the YouTube. The presentations is available on GEWEX YouTube channel, and then our future presenters. Keynote speakers, we have Dr. Murad Khani in November. If you guys continue supporting our meeting, and please join us in November as well. So anything else, you guys? Josh?
everything else, just thanks again, Ben, for coming, and we hope you keep you coming, keep you attending, and then hopefully we'll get you into a group and we'll
Yes.
working on some of these things. I think it'd be great.
Sure. Ben, if you could send us a draft of email or whatever for Japan Geoscience Conference, we would be happy to connect you to GEWEX listserv so that they can, distribute to their listserv. So be somebody interested in attending the meeting, helping with this session and all. Yeah.
Okay, I will. Yeah, thank you.
Yeah, great. Thank you again, Ben.
Yep.
Thank you, Josh.
Thanks for getting up early. I know it's early there, so
Yes. Have a good week.
awesome. Well, have a great day and a great weekend, everyone. And yeah, we'll see you again in a month, if not sooner.
Yes.
Right.
Thank you.